Okay. Hello. Okay. I think everyone already ready, right?
Yes, Ajahn.
Yes, Ajahn.
Okay. Can we start now?
Yes, Ajahn.
Okay, I will. Okay, open my Microsoft PowerPoint in there. Okay. Okay, before we go to the next part, okay, I will give you some solution, okay, first, okay, yeah. This solution, did I already provide you?
No, Ajahn, no.
Not yet.
Not yet, nah. Okay. This is the first question in the problem, in the practice, okay. I think in the previous, I give you some problem in the blackboard already. Okay, now we give you a little bit solution. Okay, even though I cannot, due to the time limitation, I cannot provide all solution. Okay, I will try to give you as much as, okay, in the limit of time. Okay, in this case, okay, xt is the pink one and ht is the green one. Okay, the questions give you xt, okay, in the mathematics form. Okay, you write them, you express them, draw them in the graphical form in here in the pink one, and ht is the same. In this case, you can see that, okay, xt is more complex than ht. Therefore, in this case, you will fix xt, right? And you will process ht instead. Okay, the first step for the convolution, after you drawing the graph completely, you change every t to be tall here, to be tall for both xt and ht to be ht to be x tall, ht to be h tall. Okay, and after that you determine its time reversal. Okay, the time reversal of ht. Okay, you flip respect to vertical axis. Okay, to vertical axis is here. Now, after you fix them, okay, you will fix the pink one first, okay, and okay, the pink ones, okay, in this form, and the green one in here. Now you move the green one in the most left hand, okay. If t equal to minus infinity is at this location. Okay. Now try to see that how many intersection pattern it has. Okay. When you observe them clearly, you can see that. Okay. Okay. The first length is between minus infinity to 0. Okay. Minus infinity to 0. Okay. It have no intersection yet. Okay. No intersection yet. Now, between 0 and 1, the intersection is start to intersect for the first rectangle. Okay. For the first rectangle. You can see that until it full intersects. Okay. Until it full intersects. Okay. The third one is when the intersection is starting to depart. Okay. Between, in this case, t is equal between 1 and 2. Between 1 and 2. Okay. Between 1 and 2. Okay. And the next step, okay, you can see that the third is already leave the first rectangle, but it start to, okay, when it's perfectly departed from the first rectangle, it start to intersect with the second rectangle. Okay. The fourth integration is applied for 2 and 3 is here, between 2 and 3. Okay. And the fifth integration is start for during between 3 and 4 when the green rectangle start to depart from the pink one. Okay. And now for the last one is when it perfectly leave. Okay. It have no intersection anymore. Okay. When it have no intersection anymore. Okay. From 4 to infinity. Now you can see that in this case, okay, the integration can separate up to 6, okay, but the first one and the last one equal to 0, right? Equal to 0, okay. You concern only the middle, okay, the second, the third, the fourth, and the fifth one, okay. The first one we can go fastly. The first integration is applied from minus infinity to 0, yeah, from minus infinity to 0. Okay, the pink one is fixed in here. Okay, the green one is here. We assume that, okay, in this case, t, any value between minus infinity and the 0. In this case, we plot them to be minus 1.5 or 2.5, depend on you. Okay, okay. For this case, you can observe that, okay, for time less than 0, the pink equal to 0. Therefore, the multiplication of them equal to 0 too. And when time greater than 0, the green equal to 0. Okay. It give you here. Okay, you integrate 0, respect to tau, give you 0 all. Okay, therefore the result of the first integration strength equal to 0. Okay, yt equal to 0, but it's 0 not all. Okay, it's 0 between when t equal to minus infinity to 0. Minus infinity to 0. Okay, you get the first one. But the second, the third, the fourth, and the fifth one is not easy like the first one. Okay, the second one, in this case, when t is shift between 0 and 1, in this case, if we fix t to be for easy for getting, okay, we set them to be 0.5. Okay, and at this point equal to t. Okay, multiply between the pink and the green one. Okay, the pink and the green one. Okay, you can see that in this graph, okay, for time less than 0, the pink equal to 0 all, therefore the result of the multiplication equal to 0. And in this case, for time greater than this point, greater than the green, okay, this t, if it greater than t, the green equal to 0, the result all 0 too. Okay, now the integration can reduce to be here. Now the integration, you can separate them in the 3 zones of the integration from minus infinity to 0, 0 to t, and t to infinity. Okay, now you can formulate in the equation is about here from minus infinity to 0. Okay, 0 to t and t to infinity. The first and the last equal to 0. You integrate 0, give you 0. Okay, only the middle you integrate 1. You integrate 1, give you respect to tau, give you tau. And you substitute the range between 0 and t. Okay, 0 and t, you get t. Yt equal to t. okay, it equal to t only when t is between 0 and 1. Okay, therefore the last point is 1, right? Y1 equal to 1. Okay, y1 equal to 1 is equal to this point. Okay, therefore the graph is yt equal to t is okay, the linear graph increasing from 0 to that point. Okay, now the next one, the third integration is applied, okay, between 1 and 2. Okay, the third integration in this case between 1 and 2. Therefore, for easy for getting, okay, the intersections pattern is we set them t equal to 1.5. Okay, 1.5. Okay, and we check that. Okay, what about the intersection is between the pink and the green again? Okay, the pink and the green again. Okay, now, okay, you can see that for time less than t minus 1. Time less than t minus 1, the green equal to 1. 0, sorry, the green. When time less than t minus 1, the green equal to 0. When the green equal to 0, okay, 0 multiply anything give you 0. And for times, okay, between 1 and t, okay, the pink is 1 and the 0, and the other is a 0 all. Therefore, the result equal to here. Okay. Now in this case, the integrations, okay, can be separated into 3 regions from minus infinity to t minus 1 and t minus 1 to 1. Okay, t minus 1 to 1 and 1 to infinity. The first and the last equal to 0 again. Okay, and only the middle one. Okay, the middle one equal to here. Okay, the middle one is integrate 1 d tau give you tau, but in this case the graph is not simple. Okay, because when you substitute the range of t is from t minus 1 to 1. Okay, you substitute them give you minus t plus 2. Give you minus 3 plus 2, the graph will be linearly decreasing. The slope equal to minus 1. Okay, but the graph, okay, is have the value between 1 and 2. When you plot the graph, okay, the graph is linked between here and here. Okay, it's linearly in this shape. Okay, next one. The fourth integration is a price for between 2 and 3. Okay, and okay, we set t equal to 2.5. Be about 2.5 in this point. Okay, and you multiply between the green and the pink again. Okay, the green and the pink in this form. Okay, now for time less than 2, you can see that for time less than 2 in this case, okay, you can separate them in so many regions. Okay, 0 for time less than t minus 1 equal to 0, and between t minus 1 and 2, the green equal to 1, the green equal to 0, the pink equal to 1. The result is equal to 0 again. Okay, it's have only one zone that not 0 between 2 and t. Between 2 and t, you can see that the green equal to 1 and the pink equal to 1. Okay, the result of the multiplications of this both graph is will be show you in the orange one. Okay, the green one is here. Okay, sorry, the red one. Sorry, in the red one is here. Now, in this case, the integration can separate from minus infinity to 2, infinity to 2, and 2 to t, 2 to t, okay, and t to infinity again. Okay, now the first and the last is equal to 0. Okay, only the middle equal to 1. Okay, you substitute the range of them and you integrate them. Okay, integrate 1 d tau give you, integrate 1 d tau give you tau. Okay, give you tau, and you substitute tau from, okay, 2 to t. Okay, 2 to t is the same graph. Okay, the slope equal to 1, but is not start at the coordinate. Okay, it will be start at 2. Here. Okay, and the last point equal to 1 is here. Okay, the graph is linearly and increasing from 0 to 1. Okay, You see that? The graph will be the result of the multiplications and the integration will be show you everything. Okay. The last, okay, almost on, not last, almost. The fifth integration is a prime between 3 and 4. Okay, between 3 and 4, we set them to be 3.5. Okay, 3.5, and we try to find the result of the multiplication between x and h. Okay, for integrate them. Okay, multiply them. In this case, you can see that for time less than t minus 1, time less than t minus 1, the green equal to 0 all. Therefore, the result is 0. Okay, and for time greater than 3, time greater than 3, the pink equal to 0. It's 0 all again. Therefore, you can see that, okay, it's only between t minus 1 and 3 that not equal to 0. It's equal to 1. Okay, the integration can separate into minus infinity to t minus 1. In minus infinity to t minus 1, and t minus 1 to 3, t minus 1 to 3, and 3 to plus infinity. Okay, for this case, okay, the first and the third case equal to 0. Okay, the first and the third case equal to 0. Only the middle, integrate tau, d tau. Okay, integrate 1 d tau give you tau. Okay, and you substitute, okay, the range between t minus 1 and 3. Okay, 3 minus 1 and 3, when you substitute them, okay, give you minus t plus 4. Minus 3 plus 4 is the decreasing linear graph again. Okay, okay, it will be at the last point up here. Yt equal minus t plus 4 is between 3 and 4, only between here. Okay, and the last point equal to 0. Okay, the middle, okay, the overall graph will be shown in here. And the last one. The last one is the last integration is a prime for t is between 4 and plus infinities as shown in the following figure, and you can get here. In this case, if we plot them, is about the 4.5, for example. You can see that for the last one, it have no intersections between the green and the pink one. Okay, therefore the result of the multiplication is 0 all. Okay, you integrate 0, give you 0. Okay. Now, the last graph is about here. Okay. In the overalls, give you here 0, t is for 2, and so on. Okay, give you here. But you know that, okay, when you write that, okay, the solution will be in this form. It's not enough, okay. You must write them in the single equations closed form, okay, that I already teach you how to write them or express them into a single equation. In this case, I give you as a guideline. Okay, it change the value or change the slope. Okay, you require one term, second term, third term, fourth term, and fifth term. It's required about 5 terms. Okay, it's required about 5 terms to compound into yt to express them in the real case. Okay. We came back in here. I think after you understand, or at least if not fully understand about the convolution, you know about the idea to determine the convolution and how. The convolutions, okay, when we apply the convolutions operator, okay, we apply them on the linear and the time-invariant system. Okay, the section presents the system that have both the time-invariant and the linear property. What about okay, you know that, okay, in the system we have 6 main property. Okay, we have the memory or memoryless, causal, stable, okay, and invertible, in the linear and the time invariant. If the system is already fixed into it's a linear and it have the time invariant, okay, is defined here. Define the system described in the following block diagram. Okay, if the input signal is X, the output is Y, okay, and YT, and the system itself have the our response is HT. Okay. The system is called is a time invariant if a time shifted of the input result in the same time shifting of the output. It means you delay the input, the output will be in the same period of time. Okay, you can see that if you delay T0, input by T0, the output will be delayed by T0. Okay. The second is the linear. What about the linear? The summary of the linear is the system is a linear if the system satisfies the principle of superposition. Okay, here if you fit x1, the output equal to y1. If you fit x2, output equal to y2. If you fit x1 plus x2, output equal to y1 plus y2. It's a linear. Okay. Now, if the system have both, have the linear and the time-invariant, okay, it will be so-called LTI, linear and the time-invariant system. Why we concerned about this system? Because the system is very simple, but even though it's a symbol, but it have the accuracies and have the high accuracy enough to estimate about the real system behavior. Okay. Therefore, the several important reasons for analyzing the LTI system are as following here. In general, many real physical systems can be modeled accurately by the LTI system, such as the system that compiled by the RL, RC, or the RLC in the circuit, or the first order, second order, or the third order. Okay, that formulate in the differential equation. And the equations which are modeled from the LTI system for both continuous time system and the discrete time system are able to solve mathematically. It means you can solve them considerably easy. Okay, even though it's easy, you solve them by the differential equation. Okay, but if the system is nonlinear, you cannot use that. Okay, it's very complicated. Okay, even though it have a considerably high accuracies. Okay, and high precision, but you sacrifice by you cannot use a simple mathematics to solve it. Okay, fortunately that okay in almost all mathematics for the bachelor degree is the linear. Okay, the next one is a much information is available for both analysis and design of the LTI system. For simplicity analysis, we can model and express the mathematical a general input signal xt and the sum of the basic function x1 plus x2 or so on. Consequently, the system output or the system response yt can be modeled as the sum of the response of each basic functions or y1, y2, or y3, so on. Okay, it means if the system is if the LTI system, if the input is a very sometimes it's a complicated. Okay, instead you analyze them by seeing them as the whole input. No, you can separate them into a simple input form x1, x2, x3, x4. Okay, and when you would like to determine about the response or the output of them, you determine the response of each simple term instead. Okay, each simple term instead. This technique is not only used for the theory point of view, but it's used in the real implementation point of view. For example, today when you broadcast the signal in the 5G, we use a wideband. Okay, at the wideband range. Okay, the way to process the wideband is very complicated and very difficult. Instead, you concern them to be the wideband directly. No, you can split them into each band, and each band is a very narrow one by separate them into 10 times or 20 times, okay, or the 100 times. Each band you can find the response. Now instead you concern a single signal with the wideband. No, you may be concerned about the signal, maybe 10 or 20 signal in a very narrow band instead. When the signal is already in the narrow band, okay, the way to create the filters, the way to create the amplifiers in that range is considerably easy. Okay, that's why. Now the next one, the impulse response of the continuous signal. Okay, the impulse response representation of the continuous signals. Okay, this section present how to express the general signals xt as the function of the impulse response. Okay, the first definition of the unit functions will be following here. Okay, that I already teach you in the first chapter or the second chapter about the impulse characteristic. The second definition of the impulse is here. If you shift things by t naught, okay, you multiply by the signal equal to that signal at time t naught. Okay, from the second definition, the shifting properties of the unit impulse functions can be expressed by the following equation here. Okay, shifting by t naught is here. And From the above equation, the integral involved and impulse functions can be expressed at the following here. Okay, if we integrate both, okay, in this function, give you here. And from this property, okay, you can see that xt is not impacted by the integration, because in this case you integrate with respect to tau. Okay, xt is not impacted. Therefore, when you, okay, we give you the solution is here. You integrate impulse, give you 1. Okay, therefore it gives you xt. Therefore, a general function xt can be expressed as the function of the impulse response by this. You can see that xt, you can write them in the term of xt multiplied by the impulse response. Okay. Now for the convolution point of view, this thing will lead you to the convolution. This section presents the equation that relates the output signal and input signal for the CT-LTI system, or the continuous time, linear, and the time-invariant system. Okay, define the system described by the following block diagram and the equation first. If the input is of the system is xt, output of the system is yt, and the system is st. Okay, for the CT-LTI system, the st is denote the impulse response if the system input is the impulse function. Okay, what about the st? The st you can determine from the system. In this case, very easy. By you feed the impulse to them, the output will be equal to st. Therefore, we call st is the response from impulse, or the impulse response. Okay, after you know about st, the next step, okay, you can, if you know the system st and you know the input xt, you can determine the output. Okay, for the LTI system, the output yt can be expressed as the convolution integral between the input xt and the impulse response of the LTI system st by here. Okay, you can see that if we know xt, if you know the system st, you can find the output. Okay, you not necessary to create or build the real system is. Okay, you can determine them from the mathematics point of view. Yt equal to xt convolve with st, and this thing is called the convolution integral that you know how to compute them in the previous section. Okay, and this thing, okay, is already have the cumulative property. That's why you can fix x or s depend on which one is more complex than the other for your easy for computation. The impulse response of the LTI system st is completely mathematically describe the input and the output relationships of the system itself. Okay, the way to compute, okay, the convolution about this thing, I think I already teach you, okay, and you know how to compute them roughly, but you don't know why to use them. Okay, for the summary, we will use them in this form. Okay, system, okay, if the system is have the input xt and the system have the impulse response ht, you would like to find the output. Output equal to the convolution between x and s. Okay, you know how to determine the convolution. Okay, you fix one of them. Okay, process another one. Okay, change every t to be tau. Okay, and you try to find how many integrations pattern it have, how many intersections it have. Okay, 3, 4, or 5. Or in the previous example, we give you about the 6 intersections pattern. Okay, you integrate each intersection patterns, follow that step. Okay. Okay. Now, up until now, I think everyone already, yes. Okay. Know about the impulse, okay, know about the impulse response, about the convolution, about the LTI system well. Now for the convolution. In the previous, I teach you only how to determine the convolution directly, okay? You know the cumulative property from, okay, the technique that you can fix the easy one, fix the complex one, the complex signal, and you process the simple one. Now, how many property of the convolution? Okay, the convolution property have the same property for multiplications point of view. The first one is to have the cumulative property. The convolution integral is the symmetry with respect to x and s. Okay, you can see that you can fix either one. X convolve with s equal to s convolve with x. Okay, therefore, by use this technique, okay, we already use this technique since during we try to determine the result of the convolution, okay, by fitting the complex one and process the simple one. For an LTI system block diagram point of view, the cumulative property can be illustrated as the following figure. Okay, you know that we can show them in here, right? Xt, okay, if the system is S, okay, output equal to the convolution between X and S is here, okay. But in the graphical point of view, the block diagram point of view, or the system point of view, you can see that, okay, you know that, okay, X and S, you can, okay, sweep them, okay, sweep them. But in the mathematics, yes, you can sweep them. But in the physics world, you can see that if you flip them, what happened? Now the signal will become the system, and the system will become the signal. That it is impossible in the physics world. For example, if Xt is my voice, okay, Ht is the microphone, the amplifier, okay, output equal to the, okay, my voice will be amplified by 10 by the amplifiers, okay, by the microphone and generate here. But if you flip them, what happened? Now my voice is become the system. Is it possible? No, my voice is untouchable, right? And the amplifier of the system will be evaporated to be the signal. It's not make the sense, right? Therefore, remember that this property, the property of the convolution, you can use them to compute the convolution result, but you cannot use them to convert, okay, the block diagram point of view, because X, okay, the system always be something touchable, okay, the real implemented system, okay. The next one is the associative property. The associative property, the result convolution integral of the three or more function is independent of the order in which the convolution is performed. If you have three or four, okay, in this case you have three convolution, you can take either two first, okay. For example, in this case you can take X and S1, or you can take the S1 and S2, or you can, okay, use, okay, S2 and S1 or so on. Okay, you can see that you can use either two first. Okay, okay, or you can use here, you can see that S1 and S2, or S2 and S1. Okay, from the LTI system block diagram point of view, the associative properties can be illustrated as following here. The key for use the associative property is try to take the convolution for a simple one first. Okay, a simple one first. Okay, is here. Okay, the idea of X convolve with S1 and convolve with S2 is about this block diagram point of view, or in the system point of view. Xt, okay, pass the process of S1, okay, and the output will be fed to the S2. Therefore, overall output Yt equal to X1 convolve with S1 first to generate the output is, okay, and this output will be fed to the S2 again. Okay, and in this case, for the cumulative property, it means you can take S2 first and process S1 later. Okay, or you can merge them. Okay, S1, S2, you can merge S1 and S2 to be a single system. Okay, you can see that in this case. Okay, the associative property can use to compute the convolution result, but it cannot use in the real physics world. Why? Because here, if S1, for example, if X is the signal from the microcontroller, S1 is the amplifier, and S2 is the motor drive. Okay, you can see that S1 is already make the sense that the signal from the controller is very small in the voltage side. Therefore, you must increase them or amplify them in the suitable form, and you feed them to the motor. But the second one, what happened? You have the signal from the controller and you feed to the motor directly. What happened? The motor is not moved and never move. Okay, and the output of the motor you feed to the amplifier is not make the sense, because the output of the motor is maybe the torque form or the rotation or the displacement. Okay, that you cannot feed into the amplifier. Okay, or if you have the motor and you have the amplifier, you can merge them to be a single one. Okay, you integrate them, melding them into the single device. No, you cannot. Okay, but you can sim them to be a single device by here. Okay, The next one is the distributive property. The distributive property, the convolution integral satisfies the following equation. Okay, if x is convolved with h1 and n with x convolved with h2, okay, you can see that you can find x1 is convolved with h1 plus h2 directly. Okay, in this case, you may have the questions why we must use this property. We use this property in the both sides, from take the left hand to the right hand or right hand to the left hand in some case. Okay, for example, in the left hand, you can see that how many convolution operator you must take. In the left hand, you have two, right? This one and this one. Is mean if you compute by follow the left hand side, you must take the convolution 2 times. But if you proceed in the right hand side, you can see that the way to adding the signal is not difficult, right? Therefore, you take the convolution, it's not difficult too. Yeah. Okay, you take the convolution only one time. But sometimes, if the signal is very complicated, okay, and you cannot convolve with them directly, right? I told you in the real telecommunication, the 5G signal, okay, is very wide band, okay. The band is high enough, wide enough to transmit the multimedia. But instead, you consider them to be a large single wide band. No, we separate them into a small narrow band, maybe 10, 100, or 1,000, okay. And you transmit them in the telecommunication in each piece of the signal. Even though some band is interrupt or destroy, okay, you not necessary to resend them all again. You send only that the band that is correct. Okay. For an LTI system block diagram point of view, the distributive property can illustrate at the following figure. Okay. If the input is here, okay, feed to the H1, okay, give you output, okay, and the same input feed to the H2, okay, give you project Y by here, okay, or you see them to be a single big system, okay, a single big system, okay, and the output will be in this form, okay. You can see that in the physics point of view will be in this form, that impossible to exist in the real world. You have the motor and you have motor one, the first motor, you have the second motor. You can feel them to be a single motor? No, it's still two motor inside it, okay. Yeah, this is about the three property of the system: cumulative, associative, and distributive, okay, property. You can use them to facilitate our problem, okay, to make them easier. Now, the next one, okay, from the system. You know that the system, we have up to 6 property, okay? But in this case, if the system is already satisfied 2 property, linear and the time-invariant, therefore, we have another 4 property left for analysis, okay? The property, okay, this in the previous section, we present the several properties of the continuous time, such as the memoryless, invertible, causal, stable, time-invariant, and the linear. But for this system, if the system is already linear and the time-invariant, okay, this section investigates the other 4 properties: the memory, invertible, causal, or the stable, okay. And fortunately, that from the CT-LTI system, okay, the CT-LTI system can be completely describe the input and output characteristic by its impulse response. Therefore, all properties of the CT-LTI system can be determined from its impulse response too. Okay. Now we concern for the first one, for the memoryless. Okay. If the system output at time t0 or y t0 depend on the system input value other than x0, then the system is called the memory. Otherwise, the system is called the memoryless. But from the LTI system, the system is memoryless if and only if st equal to impulse, okay, multiplied by k. It means st will be 0 for time less than 0 and 0 for time greater than 0. For time equal to 0, it can be any value, we don't care. If the system impulse response of the system will be in this shape, in this form, it means the system is memoryless. Otherwise, the system is memory. Okay, for example, one, you can see that the second one is here. HT is 0 only for time less than 0. For time greater than 0 is not. Therefore, if it not, it means the system is memory. Okay, the next one. Okay, the next one is the same as the second case, even though it's not constant, but we don't care. We check only HT must 0 for time greater than 0. But if it's not 0, it means the system is memory. Okay. For the last one is here. Okay. The system is not 0 for. Sorry. The system is not 0 for time less than 0 and time greater than 0. Okay. Therefore, the system is memory. Okay. Next one is the invertibility. If the distinct system input xt produce the distinct system output yt, then the system is called invertible. For the invertible system, the system input xt can be determined uniquely from its system outputs yt. And for CT-LTI system, a system is invertible if its input xt can be determined from its outputs yt by using the Fourier transform or the Laplace transform. Okay, here the system is invertible if we can create some system, inverse system that cascades to the first one, and it will be cancel effect of the first one. Therefore, the system that the input will seem to be untouchable. Output equal to input. Okay, you can write in here. Okay, xt. Okay, you write here. You know that from the convolution property. Okay, xt will be convolved with the impulse response, give you xt itself. Therefore, in this case, the impulse response, the impulse function is the identity of the convolution operator. Okay. Therefore, you can see that the hi or the inverse system will be cancel the effect of ht. Therefore, if you convolve between ht and hi, give you the impulse function. Therefore, the LTI system that have the impulse response st is invertible only if the impulse response hi can determine. That satisfy the above equation. It means the system use st. We can state that the system is invertible if you can find hi that can solve its effects. Okay. Sorry. I talk too much, okay? Therefore, I drink water for a while. Now, the idea of the system. Some of you maybe think that's okay. Why? Why we must study about the invertible system? The invertible system is very important in the real communication. If you can measure the channel characteristic, okay, and you know what about the noise characteristic is, okay, you can create the system that create the inverse effect of them. Therefore, if you convolve with the original one, okay, it seems it makes the channel will be have less noise than it usually be. Can be suppress a lot of the noise. Okay. Therefore, the wireless channel today very efficiency that you can transfer the data a big data one, not the smaller data. Okay. Next one is the causality. If the current value of the output depend only on the current at the past value of the system input, then the system is a causal. Otherwise, the system is a non-causal. Okay, hence the causal system must have the impulse response 0 for time less than 0. It means for time less than 0, ht must 0. Okay, if ht is a 0, it means the system is a causal. For in this case, ht is a causal. Okay. But it's not only causal, but it's memoryless too. Okay. Next one. For st, for time less than 0, is 0. Therefore, it's causal. Okay. It's still causal. But in this case, even though it's causal, but it's memory. But it's memory. Next one is the same. St for time less than 0 is 0. It's causal. Okay. But due to time greater than 0 is not equal to 0. Therefore, it's memory. Okay, the last one is here. For ht for time less than 0 is not 0, therefore it's non-causal and it's a memory. Okay. The last one is the stability. If the system output yt remain bound for any bound system input xt, then the system is called BIBO stable. Okay. Now, from this case, we will consider the system is stable or not from the impulse response. Okay. And we can state that if you take absolute of them, okay, and you integrate them, if it's finite, if it's less than infinity, it means the system is stable. For example, in this case, you integrate the impulse function. Integrate impulse give you 1. Okay, therefore the system is stable. Okay, you integrate them, give you 1, less than infinity. But here, you integrate them, is stable or not, you're checking that. You integrate this cloud. Okay, it seems you find the area under this cloud. The height of them equal to 1, the y of them equal to infinity. Therefore, the area under this cloud equal to infinity. If you integrate them, give you infinity, the system is non-stable or unstable. Okay. Now this one, you integrate the decreasing exponential form is finite. Therefore, it gives you stable. Okay. And for the last one, if this thing is stable, this cloud is the 2 times, right? The area of the integration. Okay, the value of the integration or the area under this cloud is 2 times for the left hand. If this thing is stable, this thing is stable too. Okay. Okay. Next one.
อาจารย์ค่ะ ขอตรง stable อีกทีได้ปะคะกับ non stable
Stable, yeah, ได้ครับ Okay, for the stable, okay, stable is here. You compute this equation. Okay, if the equation you take absolute of ht first. Okay, first step you take absolute of them. Okay, second one you integrate them. Okay, if it's less than infinity, it's stable. Okay, this one, the first one is here. This graph is already positive, right? Therefore, absolute is mean you make the graph is positive. It's already positive, you integrate them. If you integrate impulse, give you 1, right? Give you 1. 1. Therefore, this graph is stable. Okay. For this one, the second one is here, right? This graph is always positive, right? Okay, beyond this horizontal axis, okay, is positive. Okay, you integrate this graph. You integrate this graph in the physicals meaning you integrate the graph, give you area under this graph, right? If it give you area under this graph, okay, you can see that. What about the area of this graph? The height of them equal to 1, right? The y of this graph, ut equal to infinity, right? It's equal to infinity. The height of them equal to 1 multiplied with the infinity, give you infinity. The area of them equal to infinity. Therefore, it's unstable. Clear? Next one. This graph in the decaying exponential, for example, e minus t, for example, st equal to e minus t. You can find the integrations, okay? E minus t, set the range from 0 to infinity, okay? Okay? This thing, okay, the result of the area, this graph is seem to be is reached to infinity, but the area of them is finite. Okay, the area of them is finite. You can integrate e minus t. Okay, you integrate them, it's finite. If it's finite, it's stable. Okay, it's not infinity. The last one is very easy. Okay, you can see that this graph, you integrate this graph. The fourth graph is double than the third one, right? Okay, therefore the area of them is 2 times. Okay, but if this graph is stable, it's finite. This graph is finite too, right? Because if this graph, if you integrate them, give you 10, for example. This graph, you integrate them, give you 20. 20 is finite or not? Finite, right? Therefore, it's still finite too. If it's finite, it means it's stable. Okay? Clear?
Yes.
yes ค่ะอาจารย์
โอเคถามได้นะ ถามได้ไม่เป็นไร เพราะว่ามันไม่เห็น จะไม่เจอตัวเป็นๆนะมันก็นะ ไม่มีอะไรก็มีอะไรต้องรีบถามนะ อินดิเกตตามนี้เท่านั้นเองอินดิเกตตามนี้นะก็คืออินดิเกตก็คือหาพื้นที่ใต้กราฟใช่ไหมก็ถ้าไฟไนท์ก็ stable เท่านั้นเองnext one okay the exercise I will give you okay I will order you to do okay and the next time okay when the class is start don't forget to remind me to give your solution clear okay I due to it's online I think it's waste your time that I order you to do okay and I don't know what about you are doing or not some maybe sleep of course it's on okay but if you are you know that it's very important to make you understand okay you try to do that okay but you maybe require some time okay because in this case I cannot go to advise each of you personally right the on-site class okay therefore I will give you assignment okay but in this class not much okay and I will provide the solution to you okay for the next time okay next one okay the next one that we frequently use in the equation that we frequently use in the engineering or the physics model okay is the differential equations model okay the differential equation is very important traditionally a continuous time LTI system are modeled by the ODE or the ordinary linear differential equation with the constant coefficient okay the first order ODE is as following here okay you can see that the order of the differential equation okay depend on okay the maximum differentials on y operator y seem to be output okay x is the input is okay a and b is only constant value okay for the nth order ODE is mean you differentiate y in time differentiate y in time and it may be compound okay it may be consist by the lower differentiate term okay n-1 or so on okay you can express them in here now I think the way to solve the differential equation okay in the general form already teach you in the EE math but in this class I will specify only the term that you can distribute in the polynomial term in here okay in this form okay this form we call them the ordinary linear differential equation with constant coefficient okay a1 a2 a1 an minus 1 bm minus 1 and so on it's only the real value constant okay therefore in this section we present the method for undetermined coefficient for determining the solution of the differential equation. The general solutions yt can be expressed as the sum of the complementary functions yc and a particular solutions yp. Okay, the way to solve them. Okay, the way to solve the differential equation yt will be comprised by two terms: the complementary yc and the particular solution yp. Okay. Now we go to the first one. The complementary functions yc. Sometimes we call them the natural response can be determined from the homogeneous equation. How to determine the homogeneous equation from the differential equation? Very simple. You kill every non-y term. Okay, the term that have no y, you set them to be 0. Okay, I will show you in the example. Okay, you can see that if you set them to be 0, what about the next step? You can distribute them. Okay, and the differential equation. Okay, the differential equation will be reduced to be here. This term we call them homogeneous equation. For the homogeneous equations, yc will be equal to, you can determine the characteristic equation that I show you, okay? And the solution is depend on, it will be in the form of EST, okay? EST, ES1T, ES2T, ES3T, ES4T. Depend on how many differential term you have. If it differentiate by 3, you have 3 terms. If it have order 5, it have 5 terms, okay? Where C1, C2, C3 to Cn is unknown coefficient that you can determine by using the initial condition, okay? Now, for the particular solution or the fourth response can determine from the way sum of the mathematical form of xt and its derivatives that are different in the form of xt, okay? if xt, if non-y term, if xt equal to 5 constant, okay, yp equal to this term and its derivative. This term is p, right, constant. You take derivative of the constant, give you 0. Therefore, it's have only this term. Okay. Next one, 3t. Okay, 3t equal to this term, right, pt, and its derivative. You take derivative of 3t, give you 3, or give you constant. Okay, give you p. Okay, 3 power 3. Okay, power 3. Okay, take derivative of 3 power 3, give you 3 power 2. Take derivative of t power 2, give you t power 1, and so on. Okay, it's here, it will be in this form. Now, if xt is a little bit more complicated, it will be in the exponential form EAT. Take derivative of EAT, give you a EAT. It's the same form, right? You set P to be the general form, okay? And P, when you can find P1, P2, P3, Pn, okay, by substitute Yp in the differential equation form, and you can extract P from that, okay? Now, if it already in the cos function, take derivative of cos, give you sine. Take derivative of sine, give you cos again. Therefore, the general solution form will be in the term of cos 3t and sine 3t, okay? If it in the form of t cos t, okay, it will be t cos t, t sine t, and only cos and only sine. Okay, this slide is only show you some term that you frequently found in the engineering. Okay, if it have more complicated than that, you try to take the derivative of the xt is, okay, and sum them. Okay, later. The unknown coefficients p of the fourth response can determine by substitutes yp in the differential equation term. Now, this is only the abstract point of view or the theoretical point of view. Okay, now, in order to make you fully understand, I will give you the example first. Okay, this example, we start by a simple example first. Okay, the next one is a little bit more complicated. Here, you can see that this case is the first order differential equation. Okay, the differential equation in this form. Y0 equal to 4 is only the initial condition that we will use them to determine C. Okay. Now in this case, you know that the first step to determine, okay, the general solutions yt can be expressed as the sum of the complementary function and a particular solution. For the complementary function, the complementary functions yc or the natural response can be determined from the homogeneous equation here. Okay. What about the homogeneous equation? You kill non-y term, right? The first term, it have y. The second term, it have y. The third term, it have no y, right? If it have no y, it means non-y term. You kill them, set them to be 0. Set them to be 0. Okay? And after that, you find the characteristic equation. How to find the characteristic equation is very simple. Okay? If you differentiate yt one time, give you s power 1. If you differentiate yt 2 times, give you s power 2. In this case, if you don't differentiate yt, s power 0. S power 0, anything power 0, give you 1. Okay. Therefore, from this characteristic equation, the differentiate yt one term, give you s. Differentiate yt no term, no differentiate them, give you only one constant. The characteristic equation give you s plus 2. Okay, therefore s equal to minus 2. And yc in this case, right, I told you before, okay, it's have the first order. If it have first order or the other one, okay, you have only one exponential form. Okay, c1 e minus st, and s equal to minus 2. Okay, okay, you get the first solution. We call them the complementary function. The next one, okay, you must determine the particular solution. The particular solution in this case, the particular solution is non-y term, and the non-y term or xt in this case equal to 2 constant, right? If it's constant, you set them to be p is a constant. The particular solutions can be determined from the weight sum of the mathematical form xt and its derivative that different in the form of xt. Okay, you substitute them in here. Okay, y, substitute them in every y. Okay, derivative, take derivative of constant, give you differentiate constant, give you 0. Okay, 2p equal to 2, therefore p equal to 1. P equal to 1. Therefore, in this case, yp equal to 1, right? Yp equal to 1, okay? Now, you already get the first solutions, okay? Complementary function and particular solution. The complementary function equal to C1 E minus 2t and particular solution equal to plus 1, okay? Plus 1 is here. Therefore, the general solution equal to the sum of them. Now, in this case, you can see that you still have one unknown, C1, and the C1 can determine from the initial condition. The questions told that, okay, if y0, okay, y at time equal to 0 equal to 4, okay, you substitute them, okay. The unknown coefficient C can be determined by using the initial condition, okay, y0 equal to here, substitute when time equal to 0, okay, yt will be equal to 4. Anything power 0 give you 1, okay, therefore C1 equal to 3, okay, substitute them back in yt will be give you here in the general form. Okay, next one, okay, next one. How to relate to, what about the differential equation that relates to the real physics system? This section describes the general solution of the differential equations model to the response of the physics system, okay? You have that, okay, if the system can expressed by the differential equation, what about the output is? The output is comprised by the complementary function and particular solution. The complementary function in the physics world, we call them the natural response or the unfolded response or the zero input response or the transient response, is dependent only on the structure of the system. Okay, YC it depends on the system structure, not depend on the input side. Okay, and the factors, okay, the exponential S1, T, S2, T, or so on. In the natural response, we call them the mode of the system. And this thing used to analyze the system is stable or not. Okay, YP is the forward response or the zero state response, or is dependent on both the system and the input. Okay, when the input is fed to the system, how it excites, okay, so on. If the input is the sine wave, you can see that if the input is a sine shape, output will be in the sine shape too. If the input is an exponential shape, okay, output will be in the exponential shape, but maybe the signal may be amplified or attenuated, okay, maybe change in the frequency, expand them or compress them, depend on the time scaling or so on. But it must be in the same shape, okay? Now, in order to make you more understand about the relationship between the system and the differential equation is here, okay? If you have the input, you have the system, okay? If the system can be expressed by the previous differential equation, okay? That show you in the example, output will be here, okay? From the previous example, the general solutions YT can be expressed in the term of the complementary function and particular solution. You can see that the complementary function will be in the decaying form. The natural response is in the term of 3e minus 2t. Okay, the decay. Okay, it have only one mode. It have only one term because it's only first order. And the forward response will be equal to 1. Okay, the blue one equal to 1. Okay, the system response. Okay, you can see that when you plot them, you can plot separate them. That here, YC will be the decaying exponential. Okay, 1 is constant. The overall will be, the red one will be here. Okay, the sum of the complementary function and particular solution. Okay. Next one, the term in the natural response. The term in the natural response is here. What about its mean? This section describes YC. We concentrate on YC or the complementary function. Or in this case, we call them the natural response, the unfolded response, the zero input response, or the transient response. That depend only on the system structure. Okay. The mathematical form of the natural response are determined by the root of the characteristic equation by here. You know that the way to determine YC, okay, you determine them from the homogeneous equation. Set not y term to be 0, okay, you get only y term, and you expand them. You can write them in the characteristic equation, and you can estimate the characteristic equation each term to be C EST, ES1T, ES2T, ESNT. Okay, this thing is called the characteristic equation, and the factors exponential SIT in the natural response YC is called the mode of the system. Okay, this section describes the different form of the system mode that can be appear in the natural response YC. Okay, how many things that exist in here? Okay, what happened to YC? How many possibility of YC is? Okay, YC, if YC is the exponential, right? If is have the real root, okay? If S is a real positive, for example, 3, E3T, okay? E3T is here, okay? Increasing exponential. If it's 0, anything power 0 give you constant, give you 1, right? Or if it's negative, it will be decreasing, okay? If S equal to negative, it will be decreasing, okay? This thing is, okay, it's the first case that, okay, if S is the real value, negative, positive, or 0, okay? Next one is for if S is a complex conjugate. If X is a complex conjugate, it depends on the real part of them. If the real part of this complex value is positive. If it's positive, it means the envelope of the signal will be increasing from time to time, but the signal itself, it will be in the sine wave, okay, in the sinusoidal waveform, but it increasing in the amplitude, okay. The second one, if the real part of them is a 0, okay, it will be sinusoidal, will be constant amplitude, okay. And the last one is this, okay, if the real part of them is negative, okay, it will be in the sinusoidal waveform, but the magnitudes or the envelope of them will be decreasing, okay. You can see that at the pole location, okay, and will be plotted in here, okay. The system is stable or not, we can check from this part, okay. And this thing is very important in the next subject, such as the feedback control or the digital feedback control, okay. The feedback control frequently concerned about the system is stable or not. The system is stable or not, it's very easy. If it expressed in the differential equation, okay, and you can find the characteristic equation of them, and you can find the root of them, okay. It will be said that, okay, the system is stable if the real part, okay, if the real part of the solution, okay, will be negative. It will be negative, it means it's only this T point, 1, 2, 3, okay. It's only the magnitudes of them. You can see that it will be decreased when time increase, okay. It will be stable, okay. For the summary, okay, if the root of the characteristic, the real part of our root of the characteristic equation is negative, then the natural response YC is val or is stable. The root of the system characteristic equation that all lie in the left half plane is the necessary and the sufficient condition for the causal CT-LTI system to be BIBO stable. Now, in order to give you more understand, okay, we will show you in here. Determine the natural response of the following differential equation, okay. From this differential equation, even though the X will be seen to be the abstract parameters, okay, it will be unknown. We don't care because we concern only the natural response. If you concern only the natural response, okay, you set non-y term to be 0, okay, X to be 0, okay, and from this differential equation, you can find the characteristic equation. Differentiate them 2 times, give you S power 2 or S squared. Differentiate them 1 time, give you S. And here, you can use the quadratic equation, okay, factorize them, okay, and you can get S. In this case, S, okay, is the second order. You have 2 terms, 2 mode, okay, and the S equal to minus 0.75 and minus 0.5. Both of them is negative. Okay, both of them is negative. It means the system is stable. Okay. Okay, the system is stable because 2 root, okay, at the minus 0.75 and 0.5 are lying in the left half plane. Okay. Now we consider for the second one. Okay? Determine the natural response of the following differential equation and determines whether the system is stable or not. The same as the previous. Okay, you determine the complementary function yc can be determined from the homogeneous equation. You set non-y term to be 0. Okay, and you get this homogeneous equation. From the homogeneous equation, you can extract the characteristic equation. Differentiate them 2 times, give you s squared. Differentiate them 1 time, give you s power 1, and so yeah. In this case, when you factorize them, okay, you can get s. S, in this case, it have 2 values. The first one equal to minus 0.75, and the second one is plus 0.5. You can see that you have 2 terms. What happened? The system is stable or not? No. The system is unstable because, okay, one of them is positive, okay, is plus 0.5. And the root at s plus 0.5 is lie in the right half of the s plane that make the system is unstable. Now, another one example. Determine the natural response of the following differential equation. Okay, you can, okay, you concern only the natural response. Therefore, you determine the complementary function yc and you set non-y term to be 0. Okay, differentiate them 3 times, give you s power 3. Okay, differentiate them 2 times, give you s power 2. Differentiate them 1 time, give you s. And here you can factorize them, but in this case you can see that you have 3 factors. The second and the third one, okay, the root of them will be the complex, but the complex we don't care. The thing that we concern, the system is stable or not, is the real part of them. All real part must be positive, but in this case the second root, okay, and the third root will be, okay, the real part of them is positive. Therefore, if it's positive, it means the system is unstable. We can summarize that the system is unstable because the root of the s at plus 0.5 and at plus 0.5 plus minus 1.9 j are lie in the right half of the s plane. Okay, and this thing is already show you in the idea. Okay, in the overall idea. Okay, okay. As 1 minute, okay, to drinking the water. Okay. The system response of the complex exponential input. Okay, in overall system that we consider only when the input is real. Okay, it is possible if the input is complex. Yes, for the linear system, the real part of the system input produce the real part. Okay, you can see that the real part of them. If x1 is a real, okay, output y1 is the real too. Okay, if x2 is the imaginary, jx2, output will be imaginary too. Therefore, from the linearity, okay, if x1 plus x2, okay, real plus imaginary, okay, give you the complex. Output will be give you the real plus imaginary too. Okay, and from the complex point of view, we will give you here the complex input for the LTI system. This section presents the response of the LTI system yt to the complex exponential input xt. Okay, if the complex one, okay, if the complex input output is the complex 2, okay, and the system is still in the differential equation linearly, okay, it can distribute in this form, okay, the differential equation order k, okay. You can distribute them by here and by here, okay. If the input is y, okay, you can distribute them to be here and here. Therefore, the output will be the ratio between output and the input will be give you the system function in the Laplace transform domain or the S domain is here. Okay. Now, the function SS is called the transfer function, is related to the impulse response HT directly. And the transfer function SS can be written directly from the system differential equation. And the system differential equations can be written directly from the transfer function too. For the LTI system, SS is a complete complete description of the input and the output characteristic of the system, regardless of the input function is. The section presents the response of the LTI system YT to the complex exponential input is. Okay. Suppose that, okay, the system input xt is a complex. Okay. If the complex, okay, you can express or you can write them in the complex exponential form here. Okay. Where phi and the omega is real. Okay. Therefore, then we can write the input in the term of the magnitudes, okay, and the exponentials, the complex exponential form in here. Okay, express them. This is by use the Euler relation Ej omega equal to cos omega plus J sin omega. Okay, distribute them, give you here. Now, suppose that S is a complex, then thus, okay, S can be written in the magnitudes and the phase angle. Then the system's outputs YT can be expressed by the following here too. Okay. You see that I can write it in this case. Okay, you can see that if the input is a complex, output will be the complex too. But okay, you can analyze them. It's the same that is the real part. Okay, it's a real, but it's separate them between the real part and the imaginary part. Okay, okay, you can write them in the complex exponential form. Okay, Ej theta equal to cos theta, J sin theta, and you can express them. Okay. Now, in the overall point of view, you can see that it's the real part, imaginary part, give you real part, imaginary part, but the system function, okay, multiply them. Okay, the real part of the system input produce the real part of the output, and the imaginary part of the input produce the imaginary part of the output too. Okay. Now, in this example, okay, determines, okay, the system response of the LTI system if the input is in the cos functions, okay, phi cos 2t plus 40 degrees, and the LTI system can be described by the following differential equation. From this system differential equation, the transfer function SS can be determined from this case, okay. You can find the system functions by use here about the Laplace transform, okay, that we will use them later, or maybe write them in the characteristic equation you get here and express them in here. Okay, suppose that the system is excited by this input xt cos theta. Okay, and in this case you can see that for S equal to J2. Okay, and substitute J2 in the system function, you will get the response at that frequencies. Okay, at that frequencies, the response will be equal to 1.5, okay, at the minus 108.5 degree. Okay, therefore the system response YT can be expressed at the following here. Okay, the inputs, okay, the input equal to 540 degree, and the input will be the input equal to here, the system SS, okay, substitute the range when S equal to J2, okay, multiply them, give you the output at that frequencies. Okay, now when you write them in the overall point of view, okay, xt is the input, phi size 2t 40 degree, the system is 1.5 at the minus 108.5 degree. Okay, the output of them will be in this form. Okay, the multiply between the input and the impulse response or the sun transfer functions. Yeah. Okay. Now, this part we will describe them later after we concentrate on the Laplace transform. Okay. We frequently convert between the system in time domain and the frequencies domain by use the Laplace or the. We will describe them later. Okay. Impulse response. This section presents the direct relationships between the system impulse response HT and the system transfer function. The same system. okay, but see in the different point of view. Input is still xt, output is still yt, okay, but the system, the top one, will be consider them in the time domain. Therefore, we can represent the system by impulse response or hg. The bottom one, okay, we consider them in the transform domain. We call them the Laplace transform, okay. You can determine the relationship between ht and hs by using the bilateral Laplace transform, okay. Therefore, for the summary, this section presents the direct relationship between the impulse response st and the system function hs, okay, for the LTI system. For the bilateral Laplace transform, SS is the bilateral Laplace transform of st directly. Okay, you can compute that. It means if you know st, you can find ss. If you know ss, you can find st. Okay, now it's all for this and oh, a minute. No. Okay. Exercise. 3.6 3.5 ทำกันยัง problem 3.5 hello
Yes.
anyone here
Yes ครับอาจารย์
จุด5กับจุด6เหรอครับอาจารย์
เดี๋ยว 5.6 5 6 7 8 and I will give you a solution in the next time. Okay, I write in the yes, I write in the meeting chat. Can you see it? 3.5, 3.6, 3.7, and 3.8. Okay, only.
Yes, sir.
Okay, only 3 questions. Okay, I think it's okay. We will. Okay, the class will be still online. Not all, not forever. Okay, read the information from the AU web. Okay, will be online until maybe 3 or 4 January, right? Okay, and when after the new year, okay, you will recheck the situation again. Okay, if the situations about the COVID is resolved, okay, you maybe take the exams on site. But if it not, I'm not sure about that. Okay, the exam may be online. Okay. มีอะไรใครจะถามอะไรไหมครับเห็นหน้าผมกันนะแม้จะไม่หล่อแต่ว่ามีบางคนชอบบ่นว่าผมไม่มีกล้องเดี๋ยวไม่มีหน้าตาเลยรู้สึกเหมือนไม่ค่อยใช่การสอนโอเคนะมีใครมีคำถามอะไรอีกไหมครับ Any question ถ้าไม่มีก็ทำ4ข้อนี้นะแล้วอย่าลืมทวงโซลูชันด้วยนะแล้วโอเค then the next time Thursday don't forget to remind me to give you about the information in the exam information. Do you want to know about the exam?
Yes.
Yes ครับอาจารย์
Yes. Yes, อาจารย์
It's only 3-1. The other is don't want to know.
Yes, อาจารย์
one ครับ
Okay.
one
Okay. See you next time. Okay. Don't forget to remind me to give you about the exam information. How many questions it is? Okay. And what about the quota for each chapter? Okay. Okay. Good luck. Dismiss.
Thank you, John. See you.
thank you ค่ะ
Thank you, sir. See you.
Thank you ครับ
ครับผม